The next reaction that we're going to talk about is the formation of acetals and ketals. Acetals and ketals are functional groups. An acetal is a functional group that's derived from an aldehyde, and so this is going to be where we have a carbon that's bonded to a carbon-containing group, a hydrogen, and two ethers, like the methoxy groups that we see here. A ketal, on the other hand, is a functional group that's derived from a ketone. And this is a functional group where we have a carbon that's bonded to two carbon-containing groups and two ethers, like you see here. One of the very first things to know about acetals and ketal is that this carbon right here, where you've got your bond to your two ethers, your carbon and your hydrogen, that's where all the chemistry happens. We see something similar for our ketal. This carbon right there where we have the two ether groups and the two carbon-containing groups, that is the carbon where all the chemistry happens. So as you're working with acetals and ketals, make sure you recognize that carbon and make sure you understand that that carbon is going to be at the center of all of the chemistry that happens throughout our mechanisms. So overall, when we look at the reactions, an aldehyde, like this one, can undergo a reaction where we're going to treat our aldehyde with an alcohol, like methanol, in the presence of an acid, like sulfuric acid, and the product that we make out of that reaction is the acetal. So aldehydes yield acetals. Similarly, if we have a ketone, like this one, and we treat this ketone with methanol and sulfuric acid, the product that we get out of this reaction looks like this. And the product we get out of this reaction is a ketal. So aldehydes give rise to acetals, ketones give rise to ketals, and if you notice the conditions of the reaction are the same, it really just matters whether this group right here is a hydrogen or whether this group right here is an alkyl group. So if we look at the mechanism for the formation of an acetal, we're starting with this aldehyde right here in the presence of an alcohol and sulfuric acid. And what we already know about the chemistry of carbonyl compounds and the chemistry of oxygens in general is that whenever we have these types of compounds under acidic conditions, that oxygen is going to protonate. So that's going to be the very first step of this mechanism, is where this oxygen picks up a proton, and we're going to get to that intermediate. Remember that this structure here has a resonance structure that shows us that we can place that positive charge at the carbon, suggesting that my carbon is going to be a very good electrophile. I have methanol in the conjugate base of sulfuric acid at this point in the reaction. So in order to react with this intermediate, I'm going to have my molecule of methanol donate electron density towards that positive charge. And this is a reversible reaction, so make sure you have reversible arrows throughout your mechanism. And when that happens, the intermediate that we get looks like this. So if we look at this tetrahedral intermediate and we look at the product, one of the things that we notice is that we've brought that first ether group in, but we need to make sure that this ether group remains bonded to the carbon, so the next step we need to take is to remove this proton in order to keep that bond intact. So I can use the conjugate base of sulfuric acid to do that. And that gives me this structure right here. So this is a structure where I have a carbon that's bonded to a carbon-containing group, an alcohol, a hydrogen, and an ether. This structure is a significant intermediate in this reaction, and it has a name, and it's called the hemiacetal. So it's as though it means that we're about halfway in the mechanism. We've put half that acetal into our product. The next steps of the mechanism are going to be where we get rid of this alcohol and we're going to replace it with another equivalent of our ether. So this hemiacetal is in the presence of methanol and sulfuric acid. So methanol is not going to help us quite yet because we can't do an SN2 attack at that particular carbon. It's too sterically hindered. So the next thing that has to happen is we have to have this oxygen of the alcohol in the hemiacetal pick up a proton from that molecule of sulfuric acid. Now remember that these reactions are very much driven by equilibrium. So in the same way that this oxygen needs to pick up that proton in order to get us to that acetal product, this oxygen is also about equally as likely to pick up that proton and send us back to the beginning of this reaction as well. So if we take this productive pathway in the reaction, what's going to happen is I form this. I've protonated my alcohol, which I know makes it a good leaving group. That means that my oxygen can just take its electrons and leave. And the reason that it can take its electrons and leave is because I'm left with this intermediate. And as you look at this intermediate, I hope you recognize that this is a special intermediate because this is an intermediate that has resonance. We have 2 lone pairs on that oxygen, so we have resonance stabilization, and that's why that water molecule can take its electrons and leave, because we're left with a reasonably stable carbocation. Now, once we've formed this structure, or its resonance structure, the next thing to do is to bring in our second equivalent of the alcohol. So now that we have positive character at that carbon, I can have my alcohol attacking either this positive charge or its resonance stabilized structure, and I'll show it here. The oxygen attacks at that carbon, push the electrons up to the oxygen of that ether, and that's going to give me this structure. The only difference between this structure and the product that I need to form is the fact that I need to remove this proton. So I can use the conjugate base of sulfuric acid or a molecule of methanol to remove that proton, give the electrons to the oxygen, and that's going to give me my final product out of the reaction, which is the acetal.